This video covers content from your Chapter 3, Section 7 lecture notes. We're going to switch from graphing linear equations to graphing linear inequalities. Similar to the linear equations that we've been working on with two variables, we can also have linear inequalities with two variables. Here are some examples. Notice that these look very similar to the equations that we've been working with. We've just swapped out the equal sign for inequality symbols. A solution of a linear inequality in two variables is an ordered pair. We often write it as x, y, such that when the coordinates are substituted into the inequality, a true statement results. This is almost identical to what we said for the solution to a linear equation. Let's take a look at some examples. In example 1, we are asked to determine if the ordered pair 13, negative 42 is a solution of the inequality 2x plus 3y is less than negative 3. We want to substitute 13 for x and negative 42 for y. Instead of 2 times x, we have 2 times 13. And instead of 3 times y, we have 3 times negative 42. And all of that is less than negative 3. If this simplifies and results in a true statement, then this ordered pair is a solution of the inequality. 2 times 13 is 26, and 3 times negative 42 is negative 126. A positive 26 and a negative 126 combined is negative 100. So the question is negative 100 less than negative 3? Yes, it is. This is a true statement. So the ordered pair 13, negative 42 is a solution. When we substituted it into the inequality, we got a true statement. Now let's talk about graphing these inequalities. When we graph linear inequalities in two variables, we can have two types of solutions. Notice that our first example here, we have a less than or equal to symbol. That means that our solutions, x, y pairs, can be solutions to the equation y equals 4x minus 8, or they can be solutions to the inequality y is less than 4x minus 8. Solutions to y equals 4x minus 8 are all the ordered pairs that are on the line, just like in the previous sections. Let's talk about what this line looks like and graph it. The slope of the line is m equals 4, and we know that we have a y-intercept of 0, negative 8, because b here is negative 8. We can plot the y-intercept, 0, negative 8, and we can think of our slope as 4 over 1 to help us plot some more points using rise over run. We'll go 4 up and over 1 to find another point. Repeating this process, we can get a few more points. Since our inequality does have an equal sign as part of it, points on this line are solutions to the inequality. So let's graph the line. The other type of solutions to this inequality are values where y is less than 4x minus 8. These are going to be ordered pairs that are on one side of the line. What we need to figure out is if the solutions are on this side of the line or this side of the line. We're going to figure that out by using a test point. A test point is any ordered pair that is not on the line. If the point 0, 0 is not on the line in question, I like to choose 0, 0. It makes my life easy to plug in x equals 0 and y equals 0. When we do that, we have 0 is less than 4 times 0 minus 8. 4 times 0 is 0, so this is 0 is less than negative 8. Here's how this helps us. The point 0, 0 is here on one side of the line. When we plugged in the point 0, 0 as a test point, we got a false statement. It is not true that 0 is less than negative 8. This point is not in the solution set. That means that our solution set is the other side of the line. So we will shade the entire other side of the line that doesn't have our test point. And that's how we graph a linear inequality. Solutions to this linear inequality are points that are on the line and all the points on one side of the line. Now let's look at graphing a linear inequality with a strict inequality symbol that is without the equals sign. Notice that in this inequality, we have a strict less than symbol. That is, we need 3x minus 2y strictly less than, not equal to negative 12. Let's start by simplifying this and solving for y. Subtracting 3x from both sides, we have negative 2y is less than negative 3x minus 12. Dividing everything by negative 2, we have y is greater than, because we have to switch the sign, positive 3 over 2x plus 6. Take a moment and verify that that's correct if you don't see it right away. With the strict inequality, ordered pairs that are on the line are not solutions. But we can still use the line, and we need to use the line, to divide the xy coordinate system into two sides. Because the values on one side of the line will be our solution set. So let's graph the line, but instead of a solid line, we're going to use a dashed line. Looking at y equals 3 over 2x plus 6, we have a slope of 3 over 2 and a y-intercept of 0, positive 6. We can plot our y-intercept at 0, 6, and use the slope of 3 over 2 to plot some more points. That's a rise of 3 and a run of 2. So up 3 over 2. We can also continue the pattern in the other direction to help us sketch. Since points on this line are not solutions, we won't fill it in, we'll draw a dashed line instead. That way our line serves as a barrier, but not part of the solution set. Now we need to determine which side of this line the solution set is. So again, we will use a test point. You can test any point that you like that's not on the line. But again, I default to 0, 0 if it's not on the line. Testing our point 0, 0, we substitute x equals 0 and y equals 0. That is, we want 0 is greater than 3 over 2 times 0 plus 6. Anything times 0 is 0, so this becomes 0 is greater than 6. Again, this is not true. So once again, I chose a test point that happens to not be in the solution set. But that's okay. If that side's not in the solution set, then the other side is, and we shade the other side. And now that is how we graph the solution set to this type of linear inequality. We use the dashed line and shade the side that is the solution set. Let's skip to example 4. In example 4, part A, we have y is less than or equal to negative 4/3 x. The first thing to ask ourselves is, should the line be dashed or solid? Since our inequality is a less than or equal to, we want to draw a solid line. That is, ordered pairs on the line are part of the solution set. Our line will be y equals negative 4/3 x. That has a slope of negative 4/3, and with b equal to 0, our y-intercept is the point 0, 0. Let's sketch our line. We have a y-intercept of 0, 0, and with a slope of negative 4 over 3, I can go down 4 over 3 to plot some more points. And now I'll draw the solid line. Next, we're going to test a point. Notice that this time 0, 0 is on the line, so I cannot use it as my test point. But we can choose anything else that we'd like. My next go-to is the point 1, 1, because 1s are easy to work with, kind of like zeros. But you can use any point that you want. Substituting x equals 1 and y equals 1, we have 1 is less than or equal to negative 4/3 times 1. That is, 1 is less than or equal to negative 4/3. Unfortunately, that's again not true. So I again chose the wrong side. That side is not the solution set, it's the other side. The last thing we need to do here is shade the correct side. Since our test point gave us a false statement, we know the other side is part of the solution set. If we would have chosen negative 1 as our test point, we would have gotten a true statement. Let's look at part C. Part C is a special type of inequality. Notice that there's no y involved. This is similar to when we had x equals 6 and we got a vertical line. The first question we need to ask ourselves is, should it be dashed or solid? With a strict inequality, we know that we need to draw a dashed line because points on the line will not be part of the solution set. Let's consider our line. X equals 6 is a vertical line with an x-intercept of 6, 0. That's enough to be able to sketch the line. Step 2 is to test a point. But I think that you'll find that if you think through this inequality, you already know which side should be the solution set. We want all x values that are greater than 6. That is, we want x values to the right of 6. Let's test a point just to be sure. We think it's going to be to the right of 6, so let's choose a point to the right. Let's choose the point 8, 0, and we'll test that. Substituting x equals 8, we have 8 is greater than 6. This is a true statement, so our intuition was correct, that the right side of the line is the solution set. The last thing we need to do is shade that correct side. In part F, we have a similar but different situation. Again, we have just one variable, but this time it's y instead of x. Let's talk about this line. Because it's a strict inequality that y needs to be strictly greater than -3, we will draw a dashed line. Ordered pairs on the line are not part of the solution set. The line we're talking about here is the line y equals -3. That's a horizontal line with a y-intercept of 0, -3. We can sketch our line just from this information. Next, we will test a point to determine which side of the line is our solution set. But think about this inequality. We want y to be greater than -3. So hopefully your intuition's telling you that the solution set is everything above this line so that our y values are greater than -3. But just to be sure, we'll test a point. Let's test our point 0, 0. Substituting y equals 0 gives us the inequality 0 is greater than -3. That's true, so our test point is in the solution set. So the last thing we'll do is the appropriate shading. The solution set to this inequality is every ordered pair or every point above this dashed line. Let's finish up this lesson with one word problem. This is example 5, part B. It reads that Mark has at most $200 to spend on tickets for a charity baseball game. Tickets cost $2 for children and $5 for adults. Set up and graph the appropriate inequality. We have two types of tickets to think about here. We have children's tickets and we have adult tickets. Let's let X be the number of children's tickets that can be purchased, and let's let Y be the number of adult tickets to be purchased. If a child's ticket costs $2 and we have X of those tickets, then we have 2x as the cost of all the children's tickets. If we have Y adult tickets and they each cost $5, then the cost of all of the adult tickets is 5 times Y. Adding those together, we have the total cost of all the tickets. Now, we're told that Mark has at most $200 to spend. That means that he could spend $200 or he could spend less than $200. So we can write our inequality as 2x plus 5y needs to be less than or equal to 200. Now that we've set up our inequality, let's graph it. First, we'll consider the line. Since we don't have a strict inequality, but rather a less than or equal to symbol, we want a solid line. Points on the line will be possible solutions. The line in question has the equation 2x plus 5y equals 200. Let's solve this for y. Subtracting 2x from both sides, we have 5y equals negative 2x plus 200. Dividing everything by 5, we have y equals negative 2 over 5x plus 40. Now we know that we have a slope of negative 2 over 5 and a y-intercept at the point 0, 40. Let's think about how we should set up our graph. Since both of our x and y values represent numbers of tickets, we definitely won't need any negative values. We're going to be operating in the first quadrant only, where X and Y are both positive. Let's suppose that Mark only bought children's tickets. He could buy 100 of those, so our X scale needs to go up to at least 100. Let's make every unit on our graph worth 10 tickets. We have a y-intercept at the point 0, 40. We also have a slope of -2 over 5. So we can go down 2 and over 5. And that will help us sketch our line. Again, I don't want to go any farther than this in the left or right direction because I don't want any negative x or y values. Now that we have our line, we need to figure out which side of the line is part of the solution set. So we test a point. Does your intuition tell you which side of this line should be in the solution set? We need to keep the amount of money we're spending under a certain value, so hopefully it makes sense to you that the solution set should be under this line, spending less money, rather than above this line, spending more money. The values on this line max out Mark's budget at $200. But let's test a point just to be sure. Let's test the point 10-10. That is, purchasing 10 children's tickets and 10 adult tickets. Substituting 10 for x and 10 for y, we have 2 times 10 plus 5 times 10 is less than or equal to 200. That's 20 plus 50 is less than or equal to 200. 70 is less than or equal to 200, so we are correct that what's underneath this line is the solution set. That is, any point inside this shaded region is part of the solution set. Mark can purchase 40 kid tickets and 10 adult tickets, for example, and any combination that lands the ordered pair in this shaded region or on the line. And with that, I'll conclude this video lecture.